From previous session, we limit the mechanical energy to only the kinetics energies. So in this part, we gonna include all the mechanical energy, which is you already have the kinetics energy, potential energy due to the gravitational potential energy, and also the spring potential energy as well, or elastic potential energy. These are called the mechanical energy. So if we sum up, we have the total energy that we consider, and with the non-conservative force here, this is mean we have some friction happen. Friction is an example of non-conservative force. As we did state in our previous session already, the conservative force is mean when you part integration of that conservative force with the direction, you have the net force as zeros. For the non-conservative force or dissipative force, like the friction, when you integrate the closed path, that means you have value is not equal to zeros. So no matter how, you still have this as the work of friction that happen in the system. If you consider in the non-conservative force system like this, you have the external work, you have to subtract with the work that's done by the friction as well. And this minus sign due to the direction of friction is opposite to the direction of the displacement. So this part is equal to the change of energy of the system. Or you have the sigma E2 minus sigma E1, since all the sigma E is your total mechanical energy. Or all these both not only the kinetics energy, also involved with the potential energy as well. So as you look after, if the system are combined with the isolated system, there's no external work involved, you still use the conservation of energy, right? Since if it's non-isolated, you have to predetermine the external work, or this is due to the total energy transfer linked to the change of the energy, the total mechanical energy. And as I said, you look after all possible energy that involved with these kind of phenomena. And this may be due to the external force or due to some friction. It depends on the scenario. As you see here, this guy ski solely due to the gravitational and initial velocities, right? There's no additional force involved. But when you see the motocross here, there's a force that comes from the engine, right? So this force is kind of like the external force that have this bike, the mountain bike or motocross, go through all these dunes. So now we will look into more interesting problem involve the whole system. This is the first one. If you looking after this connect block and by this part with the spring and this mass hold with this string, so this is the massless string, right? And this object is going downward due to the gravitational force M2G, like this. So you would like to calculate the coefficients of the kinetic friction between the blocks M1 and surface. So in this plane you have the friction, it's not equal to 0, so you have the kinetic friction over here. So when you look through the whole system, what you have seen the spring bind to this object, and this object was pulled by the mass m2, this is m1, on the ground like this. We write this, and the friction is over here. The initial state is all these as rest and have a height h. What the time change, that means this object moving further, right? And cross this, and this m2 go down to the lower position, which is on the reference. That means the spring have some extension for h in m1. Not only the extension of the spring, is also some friction happen after motion. So we now consider with these two scenarios. So in sigma E1 and sigma E2, the change of this system is your E2 minus E1 is going toward the friction, since you don't have any external force involved in this part. So this is gonna equal to the friction. So this is the system that you call is as the isolated system with the friction, right? And all your sigma E here, you also have some potential energy involved in this part as well. So what you have in the first one, you have the potential energy here, which is the gravitational potential energy. You don't have any elastic potential energy. But from this part, you will have the potential energy, not from the gravitational, but it's from the spring or elastic potential. That is now what you have here. And what is happening here is happen at rest. So there's no velocity involved in these two parts. So your delta E is your elastic potential energy, which is US in the system 2 here, minus with UG in the system 1, that equal to FD. So your S is 1/2 kx squared, right? Minus with UG, which is mgh, equal to FD. Since the spring is due to the M1, so note that this is due to the M1 part. And your mg here is due to the M2. So write this properly as M2. X, the change is the height. So finally you get 1/2 k h squared minus m2gh equal to FD. Since F over here is the frictions, you have the balance of the force over here, like a neutron, the normal force, and the m1g here. So from mu n, you have n as the m1g, and d is the distance that this object moving, which is h, right? Because this moving as a d distance, so it's a h as a distance. So now you can see h can get rid of each other out. So you would like to determine the mu, so just realign this term. So mu is now equal to 1/m1g and 1/2 kh minus m2g. This is how you determine the mu k. So this is the final result. As you can see, in this system involved with the change of potential energy, and you can determine this and the energy in the isolate system with the friction, all energy transfer to the work that done from the frictions. And finally, you can determine the kinetic coefficients, the coefficients of the kinetic frictions between block M1 and the surface. So now, if you would like to determine in another stage, for example, this block initially have velocity VA. That means it have the kinetics energy at position A as 1 over 2 mv squared. And this energy gonna transfer to this part in part B, rather than you have only kinetics energy. It will have both kinetic energy and the elastic potential energy as well. Since this system is compressed for xb from this is an equilibrium position, zeros. When it moving forward and now this position there's no velocity, all the energy from initially Ka transfer to the elastic potential energy in position C. So all the energy go to 1 over 2 kx squared. And afterward, after this is had pushing to the maximum position, is releasing back. So this means from the C position, all the kinetics energy, all the elastic potential energy change to the kinetics energy. So in this position, if position A is at the same position as D, and all this system is conserved, that means you have the kinetic position D equal to kinetic position A. So from this diagram, we predetermine that there's no frictions involved in A condition. So now the block A having mass, this is the mass of block A, then with this initial velocity, and the spring is like a massless springs. So with K equal to 50 Newton per meter. So now we consider this state as a frictionless system first in A. So what you have here, if you would like to calculate the maximum compression, that is your X max in the system, how can you determine it? So looking at the system A, and you have seen all these, it look like the isolated system, right? And without friction, so that you use the concept of energy, right? Sigma E1 equal to sigma E2. This is the conservation of energy. Now you can apply with it. So on which state you would like to investigate from A to C, because C you have the maximum compression. So you have sigma EA equal to sigma EC. Now, and EA is 1 over 2 MA VA squared equal to 1 over 2 K X max squared. So your X max is equal to the square root of M over K and multiply with VA. Right, we arrange this term. So now you sub all the information you know in the mass of this one is 0.8 and the K is 50 and V is 1.2 square. So now you get the maximum compression from this case is equal to 0.15 in meter. This is the maximum compression. Moreover, if you would like to determine the in the next sub question, as you want to find the maximum compression in the springs in the XC, how about it if now you have the friction involved into the system? Initially there is no friction, but in this case with the frictions. So now we will determine it. So now with this case, that means now on the floor is already have some resistance, right? The mu k is equal to 0.5. And you said the initial velocity is still VA is equal to 1.2 meter per second. We would like to determine X max in this case again, the XC. So with this, now you have the isolate system with the friction. With friction, you will now get used to how to determine whether it's isolate or non-isolate system already, right? If it's non-isolate, I mean you have the external force involved into it, but in this case it's isolated system. So with this, you will have the change of energy in the system equal to the energy transfer, which is FD, and this is the change of energy from the when you have the terminal compared to the initial one minus FD, and this is from C position. I'll rewrite properly. This is supposed to be EC, and this is supposed to be EA, right? From position A to C. So now you can determine the maximum compression that relate to the mu k that we now introduce in. So this part, so you can rewrite as the mu k n, which is mg d, and the d is the displacement that is moving. In this case is the xc. If you reconsider only immediately after it impact with the spring here. So now in this term, what is happened between C and A? So as C part, you see that is some elastic potential, which is kxc square. And how about the A is solely due to the kinetics energy mv square, which is VA. So now you get the relation of the x on the left hand side, also x in the right hand side as a quadratic. As you can see, this is x square, this is x1. If you try to rearrange the term, what you see 1 over kxc square plus mu k mg xc and minus with 1 over 2 mva square equal to 0. This is look like a quadratic equation, right? Ax square plus bx plus c equal to 0. If we would like to determine x, you can use the formula, right? X minus b plus minus root b square minus 4ac over 2a, which is in this case 2a is this one, 2a, right? So that you can determine x in this case. So I will sub all the value in just for showing you how to derive it. So I will put the line between here. If you don't want to have any a coefficients, you can divide with 1/2k to the rest, but I will sub all in. So what you get, you're gonna get 0.5, and k is the spring constant, which is 50 x square, plus the mu now is 0.5, m is 0.8, g is 9.8, x, and minus with 0.5, m is 0.8, and v square is 1.2 square. Write properly, 1.2 square. These are equal to zeros. As a quadratic, you can solve this problem, and finally you will have two values. So your x, which is the maximum compression, may be equal to 0.092 meter or minus 2.5 meter. What does this mean here? If you would like to determine the maximum compression, you would like to have this as a plus sign. If you have the minus sign over here, that means there's no compression. This is extension. So it's in different meaning. So if you want the maximum compression, so x compressed max here is equal to 0.092 meter. This is your answer. Right? You can investigate this system as an isolated system with the frictions and use the information of friction that involved in this work, and you can determine the maximum compression in this case. So this is the final part about these chapters. So it's about power. So power is the thing that you would like to quantify the energy of the work that you use in the system. So the definition of power is the chain of the work, like the work that you get involved into the system that divide by time. So unit supposed to be joule per second or watt, because your work is Fs, right? And Fs is the work, so unit can be joule or Newton meter as well. So you can redetermine the unit of power to Newton meter per second as well. So this can be Newton meter per second. So all these are unit of power. So when you consider the power term that change, this means with your limit, you have the infinitesimal of the delta t. So you can dip work. If you know the work and you dip with the times, you can find the power as well. The change of the power with the time, or in any point, like this is kind of like an average, right? And this is like as some instantaneous. So from this one, you can also find the instantaneous power as well. Instantaneous power with this case. So we can further derive this as we know the work is F dot ds inside this part. And if we have the constant force, only change is ds. And your dr or ds here compared to dt is your v. You can find the definition of force in terms of F dot v. The power is F dot v, which is power in value of the scalar quantities. You will also know another way to determine the power in terms of horsepower, which is mostly used for determine the performance of the car, or how energy that engine produced to the car. The 1 horsepower is equal to 746 watt. This dyno test can use to check how like beast of this engine are. You also known that the way to quantify the power or the consumption of the electric energy, we are using the kilowatt hour meters, since the power is work over the times. So if you would like to quantify the energies, is how you have the power that multiply with the times, and power is in kilowatt and time is in hours. This is a unit of energy consumption in kilowatt hours, which is, when you derive this, is equal to 3.6 10 to the 6th Joule. That is how 1 unit of energy consumption in Joule. This is the conversion of it. So let's go through this problem. The problem is showing you like the motor is the main thing that to drive this passenger going upward with acceleration. So you would like to determine the power consumption at the motor delivered to the lift with the constant speed of 3 meters per second. So as P equal to work over T, or delta of it. So you know d work is compared to dt is P. And we did derive this as like dt here. So F ds by dt or Fv is the way to determine the power. So in this case, if we know the force that this motor lifted up due to the tension here, we can multiply with velocity, which is this is constant velocity to lift this up when we know the power in watt unit. So how to determine the force from free body diagram? You see the elevator here rising up with the acceleration. So you can use the second law of Newton's, sigma F equal to ma. And in this part, you have T minus mg and minus F that equal to ma. So your T, which is you're going to sub T into the force over here, is equal to mg plus ma plus F. I will write it properly. Ma plus mg plus F. But you change this term to here. So now you can determine power already. The power is your summation of the force that involved into this part, right? And multiply with velocity. Since these parts have some friction as well, right? With some constant friction involved in this motor. This is the free body diagram that's already explained. So when you sub all the information in this friction is 4,000 newtons. The mass is 4. I will move it slowly. So the mass that you consider here is the total mass, or I write as the small m here, which is you have a mass of the elevator 1,600 plus the mass of the passenger 200. So 1,800 is the total mass. So you sub all the information you know in like 1,800 as a total mass, multiply with acceleration, is moving with the, in this case, it seems there is no acceleration initially. So in this case, A is 0. So lucky me. And another one, M is 1,800 with G 9.8 with some friction, which is 4,000. And V is 3 meters per second. After do all the calculation, so this, the first term is gone because there's no acceleration in this part. So you finally find the power for the A condition equal to 6.49 multiply with 10 to the 4 in watt unit. This is how you determine the power that used in this system when there's no acceleration involved for lifting this elevator. However, in another case, in case B, there's difference. So now case B is moving with some acceleration that I already stated. So with the second law of Newton's, rather than you have in the first law, like frame of inertia in the A problem. So in this problem, you have sigma F equal to ma, right? And we already derived this, so we re-derive it again. So T is rising up and total mass is going downward with some frictions. So you got T minus with F and minus with mg equal to ma, and your T is equal to ma plus mg plus F. Since you like to determine the power consumption here, and P equal to Fv is what you already know, and the F is what this motor pulling, which is, you will see the motor pulling with the string tension here. So you sub T in that ma plus mg plus F and multiply with V. So now Pu have to consider the acceleration in this part. So you have 1800 with acceleration, which is, this is the acceleration in the upward direction. So it's 1. And plus 1800 multiplied with G. So this is 9.8. And plus F, which is 4000. Now this is going to be simple now because you sub everything in and it's still at the constant speed v, right? Or you would like to determine at any velocity v, so you left v over here. So after doing a calculation, so this term you're gonna get 2.34 10 to the 4 multiplied with 10 to the 4 as a v. If you would like to redetermine P at V equal to 3 meters per second, that means you sub the V into the term that you already found, and these 3. So finally, what you get here is equal to 7.02 10 to 4 in watt.